Good evening. Thank you, Mike. Thanks a lot for kicking it off. Thanks Encore, thanks GitHub for not just hosting our code, but also people. It's great. Thanks everybody for coming, showing up. This is a bit of a story, a small story about real world, like physical world data and how edge AI is interesting and important in that context. The title is like half serious. It's actually almost serious. So we'll get there. And yeah, I'm part of a small startup company, Vivid Machines. We're kind of I would say, like a full stack edge AI company. We're basically building everything end to end. We own the hardware, we build the hardware, all the infrastructure around that. We build models, we collect lots of data and deploy that to solve some interesting real world and real time problems also. This is myself. I spent about 15 years in kind of the AI space. People wouldn't call it AI back then, so it was kind of before it was a thing. Did some hardware stuff, also developed some chips for neural network inference, also before anybody was interested in that, so also moved away before anybody got interested. And was one of Yoshua Bengio's postdocs for a while, so worked in some of the big research labs doing a bunch of different AI things, really. But with the company, we're now really trying to do some slightly more practical things, real world, real-time inference, and all that stuff. And I'll talk a bit about that, but it's AI after hours. We're all interested in AI, how to build better AI systems, better products, better models. And there's really kind of three main ingredients. Architecture is almost not as important anymore. It used to be more important, but now it's mostly like you take a transformer and throw it at your problem. It's kind of universal enough to do pretty much everything. Compute is still really important. I mean, we see that with the big infrastructure deals that are happening these days. But even all the compute in the world can't really solve your problems if you don't have the corresponding data. So in the end, progress is really driven or fueled by data, like lots of data, and more for some problems than for others, but in general, data is really key. And these days, of course, for many problems, you find data on the internet, and that's kind of what's happening. You download the internet, you train your model on that, and you can solve all kinds of interesting stuff. But there's also many like other real-world tasks or problems where that doesn't work, because the data is not on the internet. You can't just download it. It just has never been captured. Like, here's an example of it's like a commercial fruit farm, an apple orchard, as you would find it in the Northwest in the US, or also in the East, actually. I think this one is in Washington State. And these operations are massive. It's thousands of acres, thousands of football fields. And to achieve good results, you really need like a granular understanding, ideally, of all these plants. And people don't really have, like, people put a handful of people into the orchard, they look at a few trees, use that knowledge or that information to make decisions. So it's mediocre results generally. And AI could play a big role there, for example, to analyze all these crops if you had all that right data. And that's actually one of the problems we're working on. So for something like this, it's not enough to just look at one farm or one orchard, because you go to the neighboring orchard, it looks completely different. There are different tree types. Everybody grows their things in different ways. And then around the world, everything looks different every time, wherever you go. No farm is exactly the same as the next. So to even capture like a small representative sample of that distribution, you really have to be in many different places to capture interesting information. And on top of that, this type of data, and it's the case for many other applications, so many other domains as well, is non-stationary, so it changes every day. Essentially, you look at the trees today, you look at it next week, it looks completely different, and then throughout the season, throughout the year, you go from buds to blossom to fruit and bigger fruit and harvest and dormancy, and so many different cases, so many different weather conditions and soil, all kinds of stuff adds up. So the product of this is a pretty massive number and massive amount of examples you would need to really capture some of that distribution. And of course, you don't really have to capture, or we don't have to capture all the possible states or all the possible examples, because that's why we do machine learning. we build models so we can generalize to unseen data or unseen settings, but still you need a somewhat representative sample of that distribution to build good models. And of course, these are just 2 or 3 of the dimensions. There's many more, like in apples alone, there's hundreds of different varieties that people grow. There's different like trellis systems, the ways people set up the tree, different row width, different tree spacing, different rootstocks. Tree age, of course, can be anything between 0 and 40 years and so on. So lots of stuff to capture. And so the way we think about it, or the way I think about it, is really the most reasonable approach to capture sort of that type of data. And this is one example, but in many other places as well, is to try to deploy some kind of application, some kind of product that people use in these settings that essentially lets you deploy or get some distribution, deploy some number of systems that capture more data, that again feed into better domain-specific models, and that again feed into more interesting or more useful applications, so you get more distribution and so on. So that's kind of a self-reinforcing cycle that we're looking for, and really starting with some simple application and over time growing that into more advanced ones that add more value and so on. Because there's really no way to, as a small startup in this case, to go to all the possible orchards and all possible times in the year and so on. So we kind of have to achieve that sort of distribution. And I'm mostly thinking about this sort of in the context of industrial applications, but of course the same thing happens in a consumer context. Like what looks like an electric vehicle to the customer is actually also a massive data collection operation from the perspective of the vendor. Or similar to the Ray-Ban glasses, like a cool gadget to the customer, but it also actually captures massive amounts of data that are really useful for robotics applications. So that happens in all kinds of places. And back to this example, farming is really hard. It's essentially a sequence of very risky, very difficult decisions. If you get them wrong, you can lose your whole crop. You go bankrupt, so that's not good. So you really need a good understanding to apply the right treatment to all the different plants, and there's lots of variability across these settings, so you don't ideally apply the same thing to all of them. Computer vision and AI can help, and for these settings, you really need to be at the edge, because there's no way, say it's a vision product that captures lots of video, there's no way to stream that to some cloud system and get an answer back in time, or even store all the data. You might need mechanisms to select interesting examples, like anomalies that you want to capture and only transfer or store that. And also there are many applications where there are real-time constraints. Like, for example, we feed the outputs of our models back into some farm equipment to do variable rate application of things like fertilizer or pesticides. And for that, you kind of also need that real-time aspect. And often in these settings, there's limited or no connectivity to like really stream all the data to the cloud. So we do that by essentially deploying these like smart vision systems. It's essentially sort of like a state-of-the-art phone, but 10x, or 10 times more throughput, 10 times more compute, 10 times more storage. Also burns 10 times as much power, is 10 times as heavy, but it doesn't really matter for these applications, because we mount them on tractors and things like that. And then, of course, all the infrastructure that comes with that, like the fleet management, software upgrade, firmware upgrades. We want to deploy models remotely. We want to, of course, extract some of the interesting data, manage that in the cloud, turn that, do all the machine learning, turn it into better models and so on, and do all that. And in practice, what we do is really mount these things on existing equipment, like tractors or sprayers, that go around on the farm anyway, scan everything, and turn that into plant-level insights. And people use that to like make very localized decisions for like labor coordination or input management. We feed it back into precision equipment as well. We can turn it, roll it up into more like downstream aggregates and statistics, like yield projections, growth rates, and all that stuff. And so that's one case, one example, but of course there are many other places where this makes sense. Like factory automation is a big thing. People often, I mean, there are real-time constraints often, but also the privacy concerns. Often people don't want to stream their manufacturing data to an external cloud or something like that, right? So you keep it in-house. Construction, for example, every construction site looks different, and you can't really find that data online on the internet. So deploying lots of sensors makes sense. There's a project in potato grading we did where we needed real-time feedback as well. Anyway, so that's just to say, is lots of room and lots of potential to capture and to tap into some of these physical world data sources that are currently completely untapped and unutilized. There's so much more data beyond the internet. And by essentially deploying these devices and doing some edge AI applications that lets you do that. And this is, yeah, kind of really what I wanted to say. So there's pros and cons, of course. It's, as I said, edge AI lets you implement applications that are otherwise not possible, and that way achieve some distribution that otherwise it's also really hard to achieve, and open up new doors and new data sources that are otherwise untapped. Of course, it adds overhead, especially the hardware component. You have to maintain the fleet. You have to communicate with devices that are often offline for unknown reasons, and figure out how to get your data back, and so on. It does get ugly, especially if you have custom hardware, especially if you mount it on tractors, for example. Hardware is hard. Software can break in so many ways. Hardware can break in many, many more ways, and maybe infinitely many, and they all happen if you wait long enough. And so it's all that overhead, and it makes it a bit harder, but also more interesting, and there's lots of potential in that space. And this is kind of all I got, and happy to take questions. I think we got some time left also. Do you want a mic? Do you want a mic?
In the slides, you showed a picture of a device with a bunch of cameras. Is that where the inference is run, or is it sent to another device?
In our case, so yes, we run it on the device, because for some applications we have real-time requirements. And also, even if we don't need results exactly real-time, it makes it much, much easier to provide a product that people are actually going to use. So it makes a difference. We give people a real-time feedback. Oh, there's something happening, as predictions coming out of it. They can actually look at some data and validate it's okay, versus storing on the device and trying to post-process that when the customer unplugs it or forgets about it, or stuff just happens. Just logistically, it makes it so much more complicated if it's not real-time. So we just try to do everything real-time.
Thank you.
So I have a question. Obviously, you need to label a lot of this data in order to train the models that you then push back to these edge devices. I'm curious, how do you determine what subset of data is sent up to your guys' cloud to then eventually be sent to labelers? How do you deal with privacy, things like that?
Yeah, I didn't talk about it. We actually do use our unlabeled data as well. So basically, we try to build sort of somewhat of a foundation model, but using all the unlabeled data internally, and then fine-tune it for specific applications downstream that we can easily deploy. So our models and our data set becomes better, even with raw, unlabeled data. And sorry, what was it? How do we label it? Was that the other question? Yeah, so we do need ground truth, of course, for some of these applications. We have a team for some things. We have people in the field actually collecting ground truth, so taking photos or generating these images and entering some ground truth information. Like it's things like for the apples, for example, it's fruit count and fruit sizes and some other stuff people care about, and associate that with the images in the field. It's you kind of have to do that because it's most of the stuff you care about is occluded. So you cannot just do it in a labeling platform. You can do some of the use cases there, but not everything. So we need some ground truth data from the field, and we also get that from customers as well. So there's for some of these applications, there's a calibration step, or that's what we call it, where people enter some ground truth information themselves to basically get better predictions, and we can use that as well. And privacy, I remember now, not really a big deal if you're in apple orchards or on farms, but yeah, in other cases, that's a bigger question.
How, I guess, going from kind of data to engineering and kind of figuring out how long a device is going to last in the field, like how have you as a business kind of figured out how to go through that QA type process that's more physical than computer oriented?
For the hardware, you mean? Mostly testing, and I mean this is the third generation of our device, and we've had it in the field for over 2 years now. So that was kind of our expected lifetime. But most of them, or pretty much all of them, we get back and they're still good. And we do so for these ag applications, it's seasonal. So we basically get the devices back after the season. We do a little bit of maintenance and send them back out in the next season. And sometimes there's small things to fix, so we do that. But they basically last all year in the field, pretty much.
Okay, so you have had some iterations and some chances to do that.
Yeah, it's not. Yeah, the first one or two generations weren't as stable, so lots of issues there. But now we're kind of at the point where it's pretty stable.
Cool, thanks.
So if privacy isn't a big issue, what is the benefit of doing inference on the device instead of sending the data to the cloud and just sending the result evaluated from the cloud?
It's in these applications, it's just too much data to really transfer everything and get results fast enough. In many places, we can't. So it's basically a video that we're recording, and people go around on the tractor for many hours in some cases. So it's just too much to. Sometimes we can store, but then transferring it is not an option really.
Any other questions?
15 seconds left.
I'll make it quick. I'm curious how specific or customized do your solutions have to be per customer versus, and like, do you have to do like a white glove onboarding and customization for each one? And what are your SLAs? Are they different for different customers, and the expectations and all of the differences here?
Yeah, at the moment we try to keep everything the same for all. I mean, we have a bunch of different things. We have apples, we have grapes, so there's some differences there, but basically everybody gets the same product, and people can achieve, like, in some sense, fine-tune it a little bit for their own situation by providing ground truth data themselves. But yeah, beyond that, it's the same product. Otherwise, it's just really hard or impossible to manage.
Great. Thanks so much, Jonathan. Let's give him one more round of applause.
Thanks, everybody.